Okay guys, let's take a look at our lesson for today. Today we're going to be looking at section 14.7, tangent planes and normal vectors. Alright, so let's take a look at this first diagram. Kind of makes common sense that our tangent lines to a particular point, P naught, they would all exist on a tangent plane. That kind of makes common sense. That's what this diagram is showing. On a level curve, when we set the function equal to some constant, it's a level curve, our tangent lines are going to be located on the tangent plane. Now let's talk about how we write the equation of a tangent plane. So if you recall from, several lessons ago, to write an equation of a plane, we need a normal vector and a point on the plane. So in this particular case, our gradient is our normal vector. And so as long as the gradient's not 0, then our gradient is a normal vector to the surface, to this surface at this particular point. And the tangent plane to the surface at P naught is going to be with this equation. So notice we have the partial derivative with respect to x evaluated at the point, and then multiplied by x minus x naught. Then we have our partial derivative with respect to y, again evaluated at that same particular point, multiplied by y minus y naught. And lastly, we have our partial derivative with respect to z, evaluated at that same point, multiplied by z minus z naught, and this whole equation is set equal to 0. Alright, so that takes care of equations for this particular equation for our tangent plane. Alright, so let's take a look at an example. So this example gives us an equation of an ellipsoid and asks us to find several things. First of all, find an equation of the tangent plane to the ellipsoid at that point 1, 2, 1. So let's do that first. Using that equation that we just talked about, I would need to find the partial derivatives for x, y, and z. So the partial derivative for x is going to be 2x. The partial derivative for y is going to be 8y. And the partial derivative for z is going to be 2z. Now we want to take those partial derivatives and evaluate them at that point 1, 2, 1 to come up with the gradient at that point. So we'll just go ahead and write. So our gradient is 2x, 8y, and 2z. And then our gradient at that point at 1, 2, 1 is 2, 16, 2. Okay, so there's our normal vector, which is the gradient. So now we can sub into our formula. We have our point. The two things we need is a point and a normal vector. So to do an equation of a plane. So I have my x component of my gradient multiplied times x minus 1, 1 being the x value of the point. Then the next segment is going to have 16. 16 is my y component of the gradient multiplied by y, and then we're going to bring in this point 2, coordinate 2, y minus 2, plus 2, which is our the z component of the gradient, times z minus 1, and the formula tells us that we set that equal to 0. So this is our answer to part A. Alright, let's look at part B. Part B is asking us to find parametric equations of the line that is normal to the ellipsoid at the point 1, 2, 1. Well, we just determined that the vector that's normal to the ellipsoid at 1, 2, 1 is the gradient. So we know that the gradient is the same thing as the normal vector, which is 2, 16, 2 at that particular point that we were interested in at 1, 2, 1. So this is at 1, 2, 1. Okay, so to write our parametric equations, if you'll recall from quite some time ago, these would be like our slopes. We think of these as slopes, these individual coordinates, and this is our point that exists on the line. So we would do 1 plus 2t would be the x equation for our parametric equation, and then y equals 2 plus 16t, and then z equals 1 plus 2t. Seeing that we get these numbers from the point and these slopes from our gradient vector, our normal vector. Alright, the last part, part C, asks us to find the acute angle that the tangent plane at the point 1, 2, 1 makes with the xy plane. Okay, so again, recalling from several units ago how to find the angle between two vectors. Let's just kind of write that formula over here just as a reminder. Remember, it's cosine theta equals, and our vectors, well, we can call it vector A dot vector B over magnitude A, magnitude B. That was the formula for some time ago to find the angle between two vectors. So if we can write, we want the tangent plane and the xy plane, the acute angle that the tangent plane makes with the xy plane. So our gradient vector, this one right here, remember that's normal to the plane. It's part of the equation of the plane. And so I'm going to dot our gradient vector, that would be my vector A, with a vector that represents the xy plane, just the simplest vector that you can come up with. Basically, if you hold the x coordinate and the y coordinate to 0, you know, that would mean that they're in the plane. Then our z coordinate is 1. So those are the vectors that I'm going to use. I'm going to use, let's see, our formula is cosine theta equals 2, 16, 2 dotted with 0, 0, 1. This is a vector on the xy plane. And so we dot those together. We're using our formula. And then we do the magnitude of each of those. And we get cosine theta equals, so we dot these together, the 2 times 0, 16 times 0, 1 times 2 is 2, and then the magnitudes of those, that would be square root of 261 times square root of 1. And so our angle measure is approximately 82.929 degrees, which would be just fine if we just take that to around 83 degrees. We don't really need to go to 3 decimal places there. All right, and that is that first example. Okay, let's take a look at our next example. So let's go to that next slide. Here, the example asks us to find an equation for a tangent plane and parametric equations for the normal line to the surface z equals x squared y at the point 2, 1, 14. First off, I'm going to write the function as a function of x, y, and z. And so that would be z minus x squared y. So that write it as a function of that first. So to get our tangent plane, we really need our gradient. I mean, that would be our normal vector, right? We want our gradient. So our gradient is going to be the partial derivative of x, which is negative 2xy, and the partial derivative of y, which is negative x squared, and then the partial derivative of z, which is 1. And there's our gradient. We want the gradient at 214, so at 214, so we substitute those values in, and we get a result of negative 4, and 1. We now have a point and a normal vector. We can now write our equation of our tangent plane, which is negative 4 times x minus 2 minus 4 times y minus 1 plus 1 times z minus 4 equals 0. And no, you don't have to write the 1. I'm just doing that so you can see where it came from. Alright, so this is our tangent plane, equation for our tangent plane. So just like we did in the previous example, we're going to write parametric equations for a normal line to the surface. So that would give us, so here's our vector, our normal vector, and here's our point. And so we write our parametrics with x equals 2 minus 4t, y equals 1 minus 4t, and z equals 4 plus t. Again, these numbers come from the point, and these numbers come from the vector. And these are our parametric equations. All right. Let's move to our, looks like our last slide. There is, your book does give an alternative equation for a tangent plane, and so let's just look at this kind of briefly. This one is created, again, using the partial derivatives at that location times x minus x naught. Partial derivative of y at that location times y minus y naught. The difference is this is the actual function value at the point. And so this is a different way to write the tangent plane to this surface at this particular point. Okay? Alright, so let's talk about intersections. In general, the intersection of two surfaces is going to be a curve in 3 space. So I'll say that one more time. In general, the intersection of two surfaces will be a curve in 3 space. And so if you have, let's kind of visualize this. I don't have a picture of this, but visualize two surfaces intersecting. Each of those surfaces is going to have a gradient, right? Each of them will have a gradient. If you have the gradient of each of the surfaces and you cross them, cross the gradients, the cross product, or actually crossing them, what you're going to get is a vector that is parallel to the tangent vector. So therefore is going to be tangent to the curve of the intersection. So if you cross the two gradients of the curves of each of our surfaces, so say a surface called F and a surface called G, you cross those gradients, you're going to get a tangent vector. It's going to be tangent to the curve of the intersection. So with all that in mind, let's take a look at what they're asking us to do. They want us to find parametric equations of the tangent line to the curve of the intersection of the paraboloid and the ellipsoid at the point 1, 1, 2. So the first thing that I want to do is rewrite those equations so that they're equal to 0. So we have x squared plus y squared minus z equals 0. And we have 3x squared plus 2y squared plus z squared minus 9 equals 0. Okay, so what we have are, we're going to call this our function of f in x, y, and z, which is going to be x squared plus y squared minus z. And let's just call this our function g in x, y, and z, 3x squared plus 2y squared plus z squared minus 9. So let's find the gradients of each of these surfaces. So the gradient of f is going to be, we're going to take the partial derivative of x and the partial derivative of y and the partial derivative of z, and that gives us our gradient for f. Let's calculate our gradient for g. So again, partial derivative of x, partial derivative of y, and partial derivative of z. Okay, let's evaluate those two gradients at our point that we're interested in at 1, 1, 2. So the gradient, f's gradient at 1, 1, 2 is going to be 2, 2, negative 1. And the gradient for g at 1, 1, 2 is going to be 6, 4, 4. Alright, so what we were talking about earlier, if we cross these, let's cross these two gradients, we're going to get a tangent vector. So we're going to cross gradient f cross g. Recall from many moons ago doing our fun crossing. So 2, 2, negative 1, 6, 4, 4. And you guys can probably do these in your sleep. So we, again, remember we cover up this part and we do our multiplication. So we get 8 plus 4i. Remember the middle one is always minus. And then 8 plus 6j plus 8 minus 12k, which gives us a vector of 12i minus 14j minus 4k. So this is the tangent vector at 1, 1, 2 to the curve of the intersection. So any scalar multiple of this vector is also going to be tangent at the point 1, 1, 2 to the curve. So we can actually simplify the vector so that it's a bit easier to work with. And so let's do that. If we divide, the entire thing by 2, we get a simplified version of this vector, which would be 6i minus 7j minus 2k. And we're going to use this to write our parametric equations. So again, with our point 1, 1, 2, our parametrics are going to be x equals 1 plus 6t, and then y equals 1 minus 7t, and then z equals 2 minus 2t. Alright, and that gives us our parametrics. There we go. And that concludes the lesson for today.